Now the meeting is being recorded. So today we have a wonderful talk, or a wonderful speaker. So far, we don't know how wonderful the talk is, but I'm pretty sure it will be totally wonderful. It's called, the speaker is Paul VanKoughnett, if I'm correct, if I'm saying it right. Maybe
close enough, yeah.
Say it again, please.
It's VanKoughnett.
VanKoughnett. Yeah, Paul VanKoughnett. I would have never guessed.
Yeah,
Thank you, Paul.
it's hard. Yeah.
So from Texas A&M University, and here we'll be talking about duality resolutions for linear groups. Please, Paul, go ahead.
Okay, great. Well, thank you all for having me. It's so great to see all of you all and give a talk in Minnesota, even if I'm not actually there. Right. So this is joint with Eva Belmont and Catherine Ray, and this problem is sort of inspired by some stuff that we were trying to understand in stable homotopy theory, but it's basically, most of this talk is going to be about sort of pure group cohomology. So if it's all right with everyone, I'm going to spend a little bit of time kind of saying some basic things about what group cohomology is and why do we care. So let's get started. So I'm going to assume that people know some algebraic topology, and so you've probably heard about K-theory before. So we can talk about reduced real and complex K-theory. For some reason, I wrote these in different ways, but they should kind of say the same thing. So we'll think about the set of real vector bundles on a space X, mod isomorphism, and identifying trivial bundles with 0. Okay, so the point of doing that is that this is a group, and likewise, you can do the same thing with complex vector bundles. And these things are maybe some of the first kind of objects of homotopy theory that people have really thought about. So one question you can ask is, let's say that you understand the KU theory of some space X, and you want to understand its KO theory. Well, you can realize that these two things are related because given a real vector bundle, you can complexify it, and this gives you a complex vector bundle. Okay. Vector bundles that you obtain this way have a special property. So complex vector bundles that occur as the complexification of some real vector bundle are isomorphic to their complex conjugates. So you can think about that as there being a group action, an action of the cyclic group C2 on KU of X. And maybe you would guess that KO of X is the fixed points of this action. So it's the set of bundles, the set of complex vector bundles that are isomorphic to their complex conjugates. So this is not quite right. The problem is that to define both of these things, you had to mod out by isomorphism. But that behaves in kind of a strange way when you take fixed points with respect to this group action. Okay. So for example, here's a picture of two different line bundles on the circle, two different real line bundles, the trivial bundle and the Mobius bundle. But these bundles have isomorphic complexification. So there's only one isomorphism class of complex line bundles on the circle. Okay. By the way, I know people always go fast in Beamer talks. So if you want me to go back and if you want to see a slide for longer, just let me know. Okay, so we can fix this problem by thinking more homotopically. So as we now know, both of these functors are represented by spectra. So there are spectra KO and KU, such that the KO theory and the KU theory of a space X are maps from the suspension spectrum of that space into these two spectra. And once we realize that, we'll remember that these are actually cohomology theories. So these two functors that I'm talking about are the zeroth pieces of some graded functors, okay, KO star and KU star. And by this same idea of sending a complex line bundle to its complex conjugate, the cyclic group of order 2 acts on the spectrum KU. And what we can do is we can take the homotopy fixed points of that action, and this gives us the spectrum KO. So in particular, if we want to compute the KO theory of X, we can follow a similar idea as we were doing earlier, but we have to modify it slightly. Instead of just thinking about the fixed points of C2 acting on KU theory, we need to think about the group cohomology of C2 acting on complex K theory. In particular, the fact that the trivial bundle and the Mobius bundle on the circle are not isomorphic is reflected as a fact about H1 of the cyclic group acting on the KU theory of the circle. Okay. So with that in mind, let me say a few basic properties about group cohomology. If you haven't thought about this much before, then there's some things to keep in mind. So first of all, there's a couple different ways to define it. So let's start with a finite group G, and let's say it acts on some module M. So what I mean by this is M is an abelian group with a G action, which is compatible with the abelian group structure, which preserves addition. So first of all, we could define this using stable homotopy theory. We could say, take the Islandberg-MacLane spectrum, which has M as its zeroth homotopy group, take the homotopy fixed points of G acting on that, and the homotopy groups of that give you the group cohomology. We could also say that G has a classifying space, BG, and M is a local system on BG. And so we could take the singular cohomology of BG with coefficients in that local system. Finally, we could define it in terms of X. So this is X out of the group algebra of, X over the group algebra of G from Z into M. Okay, these functors are the derived functors of G invariance. So M has a submodule, which is the set of things fixed by the G action, and the zeroth cohomology group is just the G invariance. The first cohomology group has a couple different descriptions, which are simplest to give in the case when M has a trivial G action. So if M has a trivial G action, H1 of G with M coefficients is the same as group homomorphisms from G into M. Since M is an abelian group, this is the same as group homomorphisms from the abelianization of G into M. So, so this is closely related to the abelianization of G. Since these are a particular example of cohomology of spaces via this definition, they have all of the same structure that cohomology of spaces has. So if you take the right coefficients, you get cup products, you have transfers, you can define homology groups, there are Steenrod operations, et cetera, et cetera. And finally, the higher cohomology of a group is torsion to the order of a group. By higher cohomology, I mean degrees greater than 0. So if the order of the group is invertible in your module, then the group, at least for finite groups, if the order of the group is invertible in the module, then the cohomology of G with M coefficients is concentrated in degree 0. Okay, so this is basically what some ways that you should think about these functors. Okay, so let's look at some more interesting examples, which are more closely related to stable homotopy theory. So first of all, let's fix n greater than or equal to 1 and a prime p. Then there's a spectrum called Morava-E theory, which has these coefficients. Okay, so a few things we should notice about this. First of all, some people are not going to have seen this before. And by the way, I have a pen that I usually use with this computer, but the battery died recently, so I'm writing with my finger. So if I look like a child, then that's why. But so this right here, this is called the Witt vectors of fp to the n. And the way that you should think about this is that the Witt vectors of fp are the p-adic numbers, zp. If we replace fp with fp to the n, then we get some finite extension of zp. Okay, but basically, if you've never seen this before, you should think of it as saying zp. So this is a power series ring over this object in some generators, and then it's an even periodic spectrum, which means that it has no odd homotopy, and all of its even homotopy groups are isomorphic, and they're isomorphic via multiplication by this thing u. Okay. So this object is of a lot of interest to people doing chromatic homotopy theory. And the reason is that it's related, or one of the reasons, I guess, is that it's related to calculating homotopy groups of spheres. So more precisely, there's a group called GN, which is the Morava stabilizer group, which I'll say more about in a second. And if you take the homotopy fixed points of this group acting on En, then you get an object called the Kn local sphere. Just like we saw for K-theory, there's a spectral sequence where the input to the spectral sequence is the group cohomology of Gn acting on this ring, which I just wrote down. And the output is the homotopy groups of this object called the Kn local sphere. The Kn local sphere is closely related to, or these homotopy groups that we're calculating are closely related to the stable homotopy groups of spheres. A bit more precisely, they're what happens if you start with the stable homotopy groups of spheres, complete at a prime p, and then pick out a piece that sort of has a certain periodicity. So if you want to know more about that, ask Craig or Tyler after the talk. So I'm not gonna be talking much about what these things are, because as I said, this is kind of like what inspired this project rather than what this project is actually about. Okay, so let me say a bit about this group GN, because it's an interesting example of the type of groups that I'm interested in. So it's a profinite group. That means it's an inverse limit of finite groups. So we're now in the world of infinite groups, and we have to modify some of our definitions slightly. Profinite groups have topologies. So what you can do is you can take the inverse limit topology of the discrete topologies on each of these finite groups in the system. And when we talk about cohomology, we have to talk about continuous cohomology with respect to this topology. Okay, so some of these definitions of group cohomology that I gave don't exactly work. The easiest one to still use is the X definition. So we can think about the completed group algebra of this profinite group, which, as the notation indicates, is somewhat analogous to replacing polynomials in the group elements with power series in the group elements. And we can take X out of that, or X over that of ZP into M. And again, by X, I mean continuous X. So these are the derived functors of continuous maps. In particular, M should probably also have a topology. It should be like a complete ZP module. Okay, I'm a very formula-driven person, so I prefer to write this group in terms of these formulas. So what this says is that this group is there's a small finite group, which is the Galois group of this field extension. And then there's a big matrix group. Okay, so these are certain matrices in GLN of the Witt vectors of Fp to the n. Again, you can think about this as being like GLN ZP. And most of the group is made out of these matrices. So in particular, this is a p-adic Lie group of dimension n squared. If you've never thought about this concept before, it's exactly what you think it is. This is a topological group. It's locally isomorphic to ZP to the n squared as a topological space. The transition maps between different copies of these are smooth, so it's a p-adic manifold. And the group operations are also smooth. Okay. And if you haven't thought about these much before, there's a reason why, which is that mostly they're pretty boring. If we forget about the group structure and just talk about p-adic manifolds are very uninteresting. So under mild hypotheses, like saying that your manifold is paracompact, any p-adic manifold is just a disjoint union of copies of ZP to the n. And it's kind of not hard to see why. So ZP, because ZP to the n is totally disconnected, it's very easy to find a closed and open neighborhood of your point that looks like this. And so you can just cover your space with these disjoint copies. Okay. P-adic Lie groups are slightly more interesting than p-adic manifolds, although the same idea that you can break the space up into disjoint copies is going to be relevant later on. Okay. So let me talk about a few examples of these Morava stabilizer groups acting on Morava E theory. So when n equals 1, E1 is the p completion of Ku. So the homotopy groups of this, this is what that formula for the homotopy groups translates into, and this U corresponds to the thing in Ku that represents Bopp periodicity. The Morava stabilizer group is ZP cross. And this is acting on P complete Ku via some version of the Adams operations. So let's first suppose that P is an odd prime. In that case, ZP cross is procyclic. By procyclic, I mean that there's a dense cyclic subgroup. Okay, so there's what's called a topological generator of this group, a generator which generates it as a profinite group. So if we call this generator gamma, then we get a finite length free resolution of the trivial module, which looks like this. And this is completely analogous to how you would compute the cohomology of Z. So if we think about the ordinary not profinite group Z, then there's a resolution of the trivial Z module that looks like this. Okay, so taking maps out of this resolution is one way to calculate the cohomology of ZP cross acting on some module. And what you get is that there's a short exact sequence for any module M. In particular, the cohomology of ZP cross is concentrated in degrees 0 and 1. So this is a group that has cohomological dimension 1, which we can see by the existence of this resolution. Okay, this is closely related to topology. So actually, this resolution can be realized as a fiber sequence of spectra. So the K1 local sphere is the homotopy fixed points of ZP cross acting on E1. And these two things are the other two things are the homotopy fixed points of the trivial group acting on E1. And so let's see. It's a pretty good exercise, I think, to calculate the homotopy groups of the K1 local sphere using that spectral sequence that I wrote down earlier. By the Adams conjecture, the fiber in this fiber sequence is related to the image of J. More precisely, its homotopy groups in positive degrees are the P completion of the image of J. Okay. So let's think about P equals 2 now. So this is a little bit more interesting because Z2 cross has 2 torsion in it. So -1 is a 2 torsion element of Z2 cross. So we shouldn't expect it to have finite cohomological dimension. In fact, we know that C2, the cyclic group of order 2, has infinite cohomological dimension. So, and we can just define a Z2 cross module by having the Z2 cross action on it factor through this cyclic group of order 2. So unlike on the previous slide, where we had this nice simple resolution, we shouldn't expect there to be a finite length free resolution of the trivial module. But what we get is something almost as good. Okay, so what we get is, so this quotient which I wrote down, Z2 cross mod plus or minus 1, this is procyclic. This is isomorphic to Z2 as a group. And so we can do the same thing that we did earlier to construct this resolution, to construct a resolution that looks like this. So this is a resolution which is of finite length, and the modules in it are not free, but they're induced from finite subgroups, from this specific finite subgroup, this group of order 2 of Z2 cross. In particular, if we take maps, so I guess now if we take X over Z2 cross from these two terms in the resolution and try to use it to compute the cohomology of Z2 cross, we get a 2-line spectral sequence, which I might have my P and my Q switched here, actually. I think this Q should be a P and the P should be a Q. But anyway, it doesn't really matter. So there's a 2-line spectral sequence where both of the lines are the group cohomology of the cyclic group of order 2 acting on your coefficients, and this computes the group cohomology of Z2 cross. And again, this is realizable by spectra. Okay, so here the fiber, this is the homotopy fixed points of the entire group Z2 cross acting on E1, and these other two things are the homotopy fixed points of this group of order 2 acting on E1. So this gives you 2 complete KO. And so again, this is sort of a modern retelling of something that was kind of known to Adams as a way to calculate the image of J. Okay, are there any questions so far? All right. So let's talk about some more complicated versions of this idea. So if you move up from height 1 to height 2, then Gors, Henmahold, and Rest constructed this resolution of the trivial G2 module, which looks like this. Okay, so this is similar to this resolution I was showing you for Z2 cross, in that each of the terms in this are induced from some finite dimensional representation of a finite subgroup. I guess I should say that G24 and SD16 are 2 finite subgroups of G2 of orders 24 and 16. And this object chi is a 1-dimensional representation of SD16. Okay, so what this lets you do, did I write it down? I guess I didn't write it down, but what this lets you do is write down a spectral sequence where the lines in the spectral sequence are either the cohomology of G24 or X'd out of this representation of SD16, and it calculates the cohomology of G2 acting on your favorite module. This is built out of a simpler resolution. So G2, oh, and I copied down the basics of the resolution up here so that you can still see them. So the group G2 splits off a central factor of Z3. And the kernel of that splitting is called G21. And there's a simpler theorem for G21 that gives you the same thing. That gives you, sorry, there's a simpler theorem for G21 out of which this more complicated theorem is proved. So there's a resolution of the trivial G21 module, which looks like this. Again, we see these two modules. These are each induced from a finite dimensional representation of a finite subgroup of G21. And so you get this resolution. Okay. So the reason why this was interesting to them is that you can, like these other resolutions we were looking at, you can realize this as a sort of diagram of spectra and use it to analyze the K2 local sphere at the prime 3. Okay, so each of these modules that we saw in the resolution is related to a certain spectrum, which is the homotopy fixed points of some finite group acting on E2. And this gives you a finite diagram whose limit is the K2 local sphere. Right, and so here's kind of what the spectral sequence looks like. So this is now a 5-line spectral sequence. It's concentrated in lines 0 through 4, and each of the terms is either the group cohomology of G24 acting on M or X'd out of this representation of SD16 into M. Okay, there's a few other examples of this that are known. Hans Werner Henn constructs these examples when n equals 2 and p is greater than or equal to 5. And again, these have a very similar form. There's some finite subgroup of G2, and you have various representations of this that produce these modules in the resolution. As in the case of p equals 3, G2 splits as a copy of ZP in a group called G21, which is why the resolution looks the way it does. But this is simpler than the case of p equals 3 because these groups don't have any p torsion. So actually, this finite subgroup F, because you're only talking about p-complete coefficients, is not going to have any higher cohomology, which means that the associated spectral sequence is very simple. At n equals 2 and p equals 2, there's a version of this which was constructed by Agnes Baudry, so she constructs her resolution just for a certain subgroup of G2, which is called S21. And there's a resolution of the trivial module for this group out of modules induced from finite subgroups of this thing. Okay, this is harder than the cases of larger primes. One of the things that makes it harder is that G2 at the prime 2 splits just as a semi-direct product, not as a direct product. And so it's less clear how to extend this to the whole group. And this resolution also has some other kind of interesting features, which I might mention later. Okay, one property that these things have in the cases which they've been observed is they have a certain sort of duality. So people tend to call these algebraic duality resolutions because of the following property. So if you have a resolution like this, then you can dualize all the things in the resolution by taking maps over the group algebra into the group algebra. All of these resolutions have the property that this dual resolution is also a resolution, and it's isomorphic to the original resolution as an isomorphism of complexes over ZP. I think in the case of, did I write this down? Yeah, in the case of Baudry's resolution, this is true up to some twist. Okay, so the question is basically, why is this happening and when else can we do it? So let's say that we have a p-adic Lie group G. Is there a finite length resolution of the trivial G module ZP by modules which are induced from finite dimensional representations of finite subgroups of G? And if so, can we say anything about what the terms in the resolution are? So for example, do we know which finite subgroups we need to use? Can we control the sizes of the representations that we need, and so on? Okay, so we are able to answer this in the case of SL2Z3. We construct a resolution which is sort of minimal size and satisfies Poincare duality in the sense I mentioned on the previous slide. And SL2Z3 is very similar to G21 for a couple of reasons. So it's a three-adic Lie group of dimension 3, just like G21 at the prime 3. It also has non-trivial 3 torsion, but a very small amount. So its 3 torsion subgroup is cyclic of order 3. Okay. This construction is a special case of a more general idea, which I'll say ahead of time we can prove doesn't always work, but I still want to tell you about it anyway. So I'm going to tell you where this resolution comes from, and then I'll say some other things we've been trying to think about these things. Okay, so so to tell you where this is coming from, I need to say a little bit more about how p-adic Lie groups work. A uniform pro-p group is a pro-p group K. I guess I didn't define the word pro-p group, but this means a limit of finite p groups that is topologically finitely generated, torsion-free, and such that the commutators of K are contained in the closure of the subgroup generated by the p powers. Okay. I'll give you some ways to think about this, but the way that you can think about this condition is if the p powers in K are sort of close to the identity, then this says that the commutators are also close to the identity. So somehow these groups are close to being abelian. Okay, so these are related to p-adic Lie groups because a profinite group is a p-adic Lie group if and only if it has an open uniform subgroup. Okay, so this is the idea of uniform groups was invented by Lubotsky and Mann, but I think many of the ingredients of this proof go back to Lazard, who thought about a closely related idea to this. One thing that you might notice about this already is that the definition of uniform pro-p group is purely group theoretic. So I haven't said anything about a p-adic manifold structure on this. So a corollary of this theorem is that a p-adic Lie group, if you forget about the p-adic manifold structure, you can recover it in a unique way, which is, I think, kind of surprising and I'm not even sure what that statement means for real Lie groups. Okay, so here are some properties that these groups have. If K is uniform of rank n, so if it's n-dimensional as a p-adic Lie group, then there's what's called a basis of K. And what that means is that every element of K can uniquely be written as a product of powers of the basis. Because we're in a pro-p group, we're allowed to take powers where the exponent lives in ZP. The other nice property is that their cohomology is very simple. So the cohomology of a uniform group is exterior on H1. And in particular, these groups always satisfy Poincare duality. So both of these properties sort of say that this group looks like ZP to the n. In particular, I think one way of phrasing this property combined with this thing I wrote down up here is that there's a filtration on K such that the associated graded is the same as the associated graded of ZP to the n. And this says that K has the same cohomology as ZP to the n. So these groups play a role analogous to the maximal torus of a real Lie group. Now, if we only think about uniform groups, it's very easy to inductively build free resolutions. So what we can do, we can actually choose these resolutions to be minimal, meaning that each of the terms is free and the rank of the terms is equal to the dimension of the homology of K in that degree. And you can build these inductively. So because you're always, because each of these modules is supposed to be free, it's very easy to define maps out of free modules. So one way of thinking about this question, which is actually, this is asking a more restrictive question than the question I originally asked, is let's start with the pro-p group. Let's pick an open uniform subgroup K, which we know exists by, once we cross out this phrase and write p-adic Lie group here instead. Okay. Great. So let G be a p-adic Lie group. And let's pick an open uniform subgroup K, which we know exists by p-adic Lie theory. Can we lift a minimal resolution for K to a resolution for G? Okay, so taking each of these factors, can we extend its K module structure to a G module structure? We'll call such a resolution K minimal. Okay, so we can think about K minimal resolutions for a general group G. Okay, and we can prove that these exist under certain hypotheses, which are somewhat restrictive. So if G is the semi-direct product of K with a finite group, and the middle dimensional homologies are projective as Q modules, then you can define this K minimal resolution. Okay, so some examples of things that satisfy these hypotheses are, first of all, if the order of Q is prime to P, and second, the group SL2Z3. And I'll say more about this specific case in a second. I guess I'll say about it on the next slide. Okay, so SL2Z3, like I said, it's three-dimensional. It has a maximal finite subgroup of order 24, which is isomorphic to SL2F3. Because SL2Z3 also surjects onto SL2F3, it splits as a semi-direct product. And SL2F3 you can also describe like this. So it's the semi-direct product of the cyclic group of order 3 acting on the quaternion group by permuting IJ and K. So the resolution looks very similar to the GHMR resolution for G21. So the outer terms are induced from the trivial representation of G24, and the middle terms are induced from a representation of this quaternion group. Okay, if you think about it, so part of the point here is that if we forget this resolution down to a resolution of K modules, these outer terms just become isomorphic to Z3 double brackets K. And the inner terms are isomorphic to Z3 double brackets K cubed. So the ranks of the things appearing are exactly the homologies of K. And again, the way this is constructed is by kind of starting with a minimal resolution of K and extending the action everywhere. So there's an associated spectral sequence where the lines in the spectral sequence are the cohomology, either the cohomology of G24 or X out of this representation of Q8, computing the cohomology of SL2Z3. As an application, there's some cohomology that we can calculate with this. So there's a two-dimensional representation of this group, which is just the standard one acting by matrix multiplication. Let's take the symmetric algebra on this representation and let's quotient it out by 3. So this is very loosely analogous to G21 acting on E2 star of V0 at the prime 3. Okay, so there's a spectral sequence that calculates this, and it turns out that the spectral sequence collapses at the E1 page. It seems more difficult to do this same computation with integral coefficients. It requires a better understanding of the differentials or the maps in the resolution. Okay, so the next thing I want to talk about is a road that we tried to go down that didn't work, but I still think it's interesting enough to talk about. So we can actually prove that it doesn't work in every case right now. But I'm mentioning this in case anyone knows a better way to think about it. So let me say a little bit more about these groups that we're considering. So if we have a uniform pro-P group K, there's a natural topology on the QP completed group algebra of K that puts the elements of K close to 1. Using this topology, we can define logarithms via this power series. Okay, so what I'm doing here is I'm taking the logarithm of a group element of K, and I can do that because this is equal to 1 plus something that's close to 0. so this power series converges in QP double brackets K. If you take the set of logarithms of group elements, then this turns out to be a Lie algebra. Okay, so it's closed under the commutator induced from the ring structure of QP double brackets K. If K is rank n, this is finite and free of rank n as a ZP module. I should also say that there's a way of defining this purely group theoretically, not using this sort of analytic procedure. And a kind of surprising fact is that the category of uniform pro-P groups is equivalent to the category of certain Lie algebras. So finite free Lie algebras over ZP, together with this property, which is analogous to a similar property in the definition of uniform pro-P group. Okay. So one thing that you can do with this is, if you want to compute the group cohomology of a uniform pro-P group, you can instead think about the Lie algebra cohomology of its Lie algebra. And there's a very explicit way to calculate Lie algebra cohomology, which is this thing called the Chevalley-Islandberg complex. So the Chevalley-Islandberg complex is a complex that looks like this. This is the exterior algebra on the Lie algebra of K, and this is the universal enveloping algebra. So this is a complex of modules over the universal enveloping algebra, which is finite length. It's functorial in K, so it's preserved by, or I guess automorphisms of K act on this complex. It has a natural cup product structure. It has duality, all coming from the exterior algebra, and the dimensions of the terms in this are just the dimensions of the exterior algebra in each degree, which are the same as the dimensions of the homology groups of K. So one thing that you could try to do is relate this somehow to a complex that calculates group homology. In particular, there's an inclusion from the group algebra of K to the universal enveloping algebra of Lie of K, with the property that once you tensor with QP, you get an isomorphism. So one could ask the question, is there a way of taking this nice functorial complex of modules over the universal enveloping algebra of Lie of K and turn it into a complex of ZPK modules, again, in a functorial way? Okay. No.
So would the functorial complex be a resolution at all, or is this still no? It's not. But...
Okay, so if you start with this and you forget down to ZP double brackets K, the problem is this inclusion is not flat. So well, I think you still get an exact sequence because you're forgetting, but what's the issue? I think the things in the exact sequence are like infinite dimensional over ZP double brackets K or something. Something weird happens. Was that the question?
I think so.
Okay, cool. Yeah. Okay. So I copied down the proposition so that people can still see it. So here's why not. So if there were, then for any K, if K was occurring as an open normal subgroup of G and G had this semi-direct product decomposition, then you could use the Q action on the Chevalley-Islandberg complex to extend this complex that you defined to a resolution of G modules. Okay, so there would be a way to define a K minimal resolution for any group of this form. And we found an example where we can't do this. So this is a two-dimensional example where you take the semi-direct product of Z3 squared and a cyclic group of order 3. And the cyclic group is acting by some non-trivial element of GL2Z3. Okay, so there's a couple questions that come out of this. One is, I've been talking about K minimal resolutions this whole time, but some of the resolutions that we knew about that inspired this project are not K minimal. So in general, there should be a way to start with some less minimal resolution and lift it to a resolution of the bigger group. And that's kind of where we're hoping to go with this, I think. And I think that's all I had to say. So I guess I ended somewhat early, but thank you all anyway.
Thank you very much, Paul. Any questions? Any more questions?
Could I ask? I always wonder, can people hear me if I just speak like this? Like you can hear me.
I can hear you. Yeah.
I could even hear Tyler in the background.
Yeah. Okay. Just wondering. So I was with what you've got on the screen at the moment. Just to ask what you mean, I'm not quite sure. So K is the subgroup of G. So when you say a K minimal resolution, do you mean a resolution that's on restriction to K is also minimal?
Yes. Yes.
Okay, that's what you mean. To be honest, I'm not quite sure why you want a K minimal resolution, because any resolution will compute cohomology. But anyway, so that's what you mean with that. And earlier on, you were you had a moment when you were you were saying that it was easy to build three resolutions for G if you've got a resolution for K, I think, or no, maybe under some circumstances. When the quotient group had order prime to P, for instance, as an example.
Yes.
And I was wondering what you meant by this, because can one not always, it is the construction you mean that you take a surjection onto K and then you take the kernel and then you find generators for that and you subject.
Yeah, that's what I mean. Yeah.
But you can always do. Is the point that maybe you've got like Nakayama's lemma and you can find what's the minimal generating set is that's the point that you're making.
Yeah.
You can always construct these things.
Right. Yeah. So this, I mean, I think this question is only like this is not very interesting for uniform groups alone. But it's interesting when you have a group that has infinite cohomological dimension, because you're still trying to build a finite length resolution of it.
So you want to build a finite resolution. Well, it would be a finite resolution of a K probably, but
yes, exactly.
P does not divide if P does not divide the order of the quotient, then you could get a finite resolution for the whole group. Yeah. Okay. One thing I was wondering is in your groups that especially I think you're considering G2, and various finite groups appear, like the semi-dihedral 16, I suppose, the structure notations notes, and also containing groups and so forth. And I think, and then you mentioned other groups like SL2 of 3 and so forth. And the only finite two groups that occur in these groups are the groups of maximal class, namely which are the dihedral, semi-dihedral, and quaternion. Are those the only finite groups, the two groups that are occurring?
What do you mean by maximal class?
Well, for two groups, it means the nilpotent class is n-1, where the group has order p to the n. But for two groups, there's a classification of those. They are the semi-dihedral, the generalized quaternion, and the dihedral. Also cyclic, is got, it obviously appears as well. But are those the only two groups that are appearing as finite subgroups of your group? I don't think any others appear.
Right. So I mean, I don't know. Like the examples of this phenomenon that I've told you about are the ones that I know about. I don't know. I believe it's known, if you think about just the Morava stabilizer groups, it's known what their finite subgroups are. And I think that they're all roughly like at the prime 2, there's something like quaternion groups or cyclic groups.
Yeah, you've got semi-dihedral as well. I would imagine, I'm just wondering out of casual interest, what subgroups would appear. And I imagine this would be the case, that these are the only finite subgroups that are appearing. I'm not
Yeah,
sure
so-
what the G24 group is, but
Right. G24, it's either. Oh, yeah, it gets complicated because there are a few different ways to define these profinite groups, but so this is either I think it's either a semi-direct product of C3 with a quaternion group or a semi-direct product of C3 with a dihedral group. Yeah.
yeah,
And
the
here I
dihedral
should-
group doesn't work because
Okay.
it doesn't have a C3 automorphism with dihedral group.
Oh, my bad. Okay. Yeah.
But the other one works. Yeah.
Yeah. Yeah.
Good. So, sorry, I'm hogging all the questions, but you
No, please.
finished early, so maybe people want
Yeah. I'm very interested in what you have to say.
There was another slide somewhere where you were mentioning a duality, and it was the duality induced by homomorphisms into the group ring.
Right.
And this duality tends to send left modules to right modules.
Mhm.
And it sends projective left modules to projective right modules, or the other way around, depending on what your convention is. And I wasn't quite sure what you were doing with this, because if you start off with a resolution of left modules, for instance, then you would finish with a resolution of right modules. And I don't see how you would use that. You can, of course, apply then a vector space duality or something as well, but then you get injected modules if you do this. Like, do you see my trouble?
I do, yeah. Can't you turn a right action into a left action by having it act through the inverse?
They are, so yes, but then if you're dealing with these infinite groups, would not the projective module become an injective module, or perhaps that doesn't happen?
I don't think so.
Yeah. Okay, maybe that works. Okay, maybe that works by letting the group act by the inverse. Okay, that would deal with the
I think that's it, and I think I forgot to put it on this slide.
yeah.
Sorry about that.
Okay, that's good. Thank you. And I think that's all the questions I've got. Thank you very much.
Other questions? Craig?
Yeah, I had a vague one.
Yeah.
So the one of the cool things in K and local homotopy theory that GHMR do with their resolution is construct exotic elements of PIC by taking their resolution and messing with it. I don't know if there is even a context in which you could try to do the same thing for your resolution of SL2Z3, but is there?
I don't know. So something like exotic elements of the Picard group of a projective line over Z3 or something.
I mean, I think the problem is there's like there's no obvious homotopical thing. Which is replacing it, but I don't know. It may be.
I don't know either, but that's a good question. I'll have to think about that. Yeah.
And then I also think Hans Werner had another finite length resolution of the stabilizer groups that's called the Centralizer Resolution.
Right.
But it's longer. I think it's like the homological dimension of the group or something like that. Can those be sort of realized in this way?
Well, so if the length is the cohomological dimension of the group, then most of these interesting groups have infinite cohomological dimension. So,
right. I guess I really mean the actual dimension, the geometry.
Oh, I see.
As a Lie group.
Yeah, I don't know how that's related to this picture. I do remember. I think it's harder to prove duality for those types of resolutions. Yeah, but other than that, I don't exactly know how it's related. But that's a good point.
I maybe I'll put the two together in saying that, like, if that is the case, then maybe you could sort of adapt the GHMR program to construct some new exotic elements of PIC by with the same sort of mixing procedure. But sorry, I've got nothing but vague.
No, that's okay. That's okay. I mean, most of yeah.
Just shut up.
No. These are yeah. So you're talking about exotic elements of whatever PIC.
Yeah.
Whatever PIC is the PIC. Yeah. I will have to think about that. I don't have anything intelligent to say right now.
Other questions?
So while we're asking about like weird things,
Mhm.
so there's these groups that you're looking at, like SL2 and Z3 and this
Mhm.
Z2. They both come from algebras, and the algebras are kind of related in some kind of Galois theoretic sense, like after
Yeah.
and the p-adics. Is there some kind of context in which these resolutions for these two different groups kind of play in the same location where you can study?
I have also wondered this, and I don't know how to. So I think it's even true that these SL2Z3 is some kind of twist of G21 as an algebraic group, but I don't know how to relate that to facts about its cohomology as a profinite group. But maybe somebody else does.
We'll try.
I mean, you could hopefully approach both of them via the Galois cohomology of the Galois group of whatever the thing they're both a form of.
Yeah.
But then,
so maybe there's a finite length resolution of that, with which both the GHMR resolution and this resolution that I defined are sort of Galois fixed points up. Maybe. Yeah, that's a good idea. I think maybe one place that this is relevant, I haven't thought about this that much, but there's this, you could try to think about the algebraic K-on local Picard group as, so this is some group of equivariant line bundles on Leuven-Tate space. And in particular, such bundles, I think, induce like they pass to the rigid analytic version of Leuven-Tate space, and then via the like period map machinery, you can turn them into GLN equivariant bundles on projective space. So maybe somehow that's a way in which the cohomology of GLN is computing something that's related to Picard groups in homotopy theory, though through a pretty like opaque procedure. Maybe that doesn't make any sense though.
wait, is that really what's going on? I thought that the GLNZ3 and the stabilizer group were related more via like a Schur-Weil duality kind of. That the GLNZ3 is acting on the level structure and but
I don't completely understand what you just said.
you're not the only person. I also did not completely understand what I just said, but
I thought you could. So I thought you could use the Gross-Hopkins period map to quotient Leuven-Tate space by a GLN action. This maps you to some object. In particular, a GN equivariant line bundle on Leuven-Tate space would map to a GLN times GN equivariant line bundle on this quotient object. And then you can lift back up the other, the Hodge-Tate period map or something to get a line bundle on a projective space.
I think I agree, but is that sort of push-pull kind of realizing both of these things as forms of the same?
Oh, yeah.
I think they're both
believe you.
Inside of a kind of cross product group. And
okay. Interesting.
Very good. Any other questions? I have a couple. If you have, I mean, the idea of using k-minimal resolutions, isn't it to basically consider as small resolutions as possible?
Right.
And you can't do a g-minimal resolution, but it's no hope. So, but k-minimal, since k is similar to a maximal torus, then probably you can do have this minimality property, right? Okay, great. And then also, were you using the Chevalier-Islandberg complex to construct a resolution or to compute the cohomology?
So I think it can be used to compute the cohomology. I was mentioning it as an idea that doesn't work for constructing the resolution, but you can use it to compute the cohomology of K, and then maybe use some Lennon-Hochschild-Serre spectral sequence to say something about the cohomology of G.
You wanted to make the coefficients smaller from the universal development algebra to something smaller, like you hoped it was. I like your proposition, the shortest proposition on Earth. But why can't you just take, I guess here the action of the Lie algebra of K on the universal development algebra is the adjoint action, right? Why can't you just take the Lie algebra itself with the adjoint action as coefficients? Smaller.
So what types of object? I mean, sorry, what do you mean by take them as coefficients?
Well, you can take any module over the universal development algebra or over the Lie algebra itself as coefficients in this Chevalier-Islandberg complex.
Right.
And instead of taking the universal development algebra, you can always take the Lie algebra itself with the adjoint action.
Okay.
This gives you a cohomology of the Lie algebra of K with coefficients. Well, in this case, probably homology of the Lie algebra of K with coefficients in the adjoint representation, right?
Right. Okay.
So wouldn't it be sort of pretty much, well, it's not the same thing, but yeah, honestly, I don't really understand why you take the universal development algebra here.
Well, I think I mean, yeah, you're right. You could replace this with any, like, I think these other complexes that you're talking about, you get by tensoring down the one that I wrote down. So, but yeah, you could tensor it down to something else.
Well, I meant to replace the universal development algebra with the Lie algebra of K.
Yeah. But I don't see. So I agree that you can do that, and that gives you something that computes the homology of the Lie algebra acting on itself. But what?
I thought that the idea of your using the universal development algebra was to pretty much do the same.
So the idea was to try to relate this to some complex of ZP double brackets K modules, something that could then be maybe lifted to something that computes G homology.
I see.
Yeah. But as I said, this doesn't work, and even in some very simple cases.
Okay.
Yeah.
I got it. Yeah. I was hoping that actually ZP double bracket K was included in the Lie algebra of K, but probably not.
It's right. The Lie algebra of K is somehow similar to K itself.
Yep.
Yeah. As a matter of fact, I mean, I defined it this way, but so this way shows you that it's in bijection with K. Yeah.
All right. Actually, I'm supposed to start another Zoom class in a different building in less than 5 minutes. So
okay.
Yeah, you better hurry. Since I'm the host, I guess I would. Well, Craig, would you like me to keep you the host? But I will still stop this session. Craig, you're muted. I don't know if you're responding. Oh, yeah, you're muted.
Sorry, yeah, that'll be fine. Thank you.
Oh, okay. Let me try to do it. Yeah, let's thank Paul for the wonderful talk, but I will make Craig the host, and so you can continue chatting to each other. Thank you so much. Okay.
Hi, Paul. I don't have anything mathematically interesting to say. I just wanted to say hi. This is Liam.
Hey.
Hey.
Okay.
Sorry, I have to go grade. Thank you for your
Oh,
help.
good luck with your grading. Yeah, good to see you.
I'm stopping this. Sorry.
Okay.